everyone.
All right. Thanks for waiting patiently for another 15 minutes for another technical, resolving technical glitches. But we're done with that, hopefully for the rest of the day. And with that, it's my pleasure to introduce Amin, who is calling from Toronto.
Yeah.
All the way. And he's going to talk about operator splitting value iteration.
Thank you so much. Hi, everyone. My name is Amin. I'm a third-year PhD student at the University of Toronto, working at Bellman. And today I'm presenting our paper at PRIPS 2022 called Operator Splitting Value Iteration. And it's a work done with my co-authors Andrew Wan, Mohammed Awalzadeh, and Amin Rakhsha from University of Toronto, Vector Institute, and Google Research. So let's start from the problem we're solving. In this work, we assume the true dynamics of the environment is P, and we assume that we do have access to P, but we assume it is expensive to access P. So whenever we want to query P, we need to pay some cost. On top of that, we also assume that we have an approximate model called P hat that is inaccurate. It's not the true dynamics, but it is cheap to use, and you don't need to pay any cost when you want to use P hat. And whenever I say query, that's what we measure the amount we use the dynamics. And this presentation is that you can pick a value function V, and through one query to P, you can get PV. So that is for each state action pair, you're getting the expected value of your chosen value function over the next state distribution. Right? And the problem is that how can you use both P and P hat, considering their difference in accuracy and the cost of usage to calculate the value functions? This can be the value function of a specific policy pi that I'm going to call the policy evaluation problem. Also, some people call it prediction problem. Or it can be the optimal value function V star that I'm going to call the control problem. As motivating examples of this scenario, we can think of, for example, robotics, where P is a very accurate simulator. For example, we do have the differential equations of physics of the ball, but doing accurate calculations with this dynamics is expensive computation. And we may want to use some more approximate, less accurate simulator, as our P hat is cheaper to use. It also connects to model-based reinforcement learning, where P is the true environment that we're interacting with. As we know, in many scenarios, it is expensive to get samples and information from the real environment. But P hat can be the model that the agent has learned, and getting samples from it is just a matter of computation, and we don't need any interactions with the environment. We can think of two main approaches in oral literature for this problem. First is to do just any planning algorithm like value iteration with the true dynamics P, which can be thought of as the basis of our model-free reinforcement learning algorithms with PQN. The good thing about this is that you're only using the accurate dynamics P, so your value function is accurate. But because you're not benefiting from the model that's given to you, you need lots of queries to P. Specifically, if you have K queries to P, your error is of the order of gamma to the power of K, which can be very slow if gamma is close to 1. The second approach that is the basis of our model-based oral algorithms, like line architecture, is to only use P hats and, for example, do value iteration. Now that you're not using P, you're not paying any cost due to using P, but P hat was inaccurate, and due to this inaccuracy, your value function will have some error. And there are not many clever ways to use both P and P hat in the literature, and that's what we are doing here. We introduce operator splitting value iteration. That, if I want to summarize the whole idea in one line, is that you use P to correct the error of planning with P hat. And by using both P and P hat, you're able to solve the problem in fewer fewer queries to P. Yeah, as you can see. So in comparison, if we have K queries to P, our error will be of the order of gamma over 1 minus gamma, gamma being the discount factor, times model error to the power of K, which means your convergence rate is now dependent on model errors. And if your model error is small enough, very small, this can be much faster than conventional value iteration that have the fixed gap. On top of that, the slides are a bit behind. On top of that, even though we are benefiting from the approximate model that has the wrong dynamics, we are not introducing any error to our final value function due to this. So we are still converging to the true value function. In the end, we generalize operator splitting value iteration, which, by the way, we also call OSVI in most of the presentation, to the sample-based setting where we only have samples from P. And we introduce OS-DYNA that shows the same benefits of OSVI in the sample-based oral setting. All right. Any questions about the problem and high-level ideas? We can start from the inspiration of our algorithm, matrix splitting, that is some method in numerical linear algebra to solve systems of linear equation, like this AX equals to B. And the idea is that you write the matrix A as M minus N for matrices M and N. And then matrix splitting gives you this iterative procedure to solve the equation. At each iteration, xk plus 1 is M inverse times B plus nxk. And if you look closely, you notice that we have M inverse in our iteration that is basically solving a system of linear equations. So the catch is that you need to be careful when you choose M and N. You should pick an N that you can calculate the inverse. So the idea is that you cannot take the inverse of A, but you can take the inverse of N, and you use matrix splitting to solve the system of equation. One other thing to know about matrix splitting is that its convergence rate depends on the choice of M and N. So better choices can lead to better convergence rate. The way it connects to our problem is that we have Bellman equations for policy evaluation. As you can see, we have I minus gamma P times V pi is equal to R pi. That's a system of linear equations. And we can potentially use matrix splitting to solve this. And we actually do. The normal value iteration that we do so often is one instantiation of matrix splitting. And that's where we have chosen M to be identity and N to be gamma P pi. Now M minus N is I minus gamma P pi that we want in our original system equation. You plug them in to the matrix splitting recipe and you get value iteration. And one other thing is that now that M is identity, we don't need to worry about calculating its inverse, and everything is good. What OSVI does is just to use p hat to find a better splitting. What we do is that we choose M to be I minus gamma p hat pi. Then N becomes gamma p pi minus gamma p hat pi to make the equality. All right? You plug them into matrix splitting recipe, and you have OSVI for policy evaluation. Yeah, so this is OSVI for policy evaluation, and we show under some conditions, I'll talk about it later, it will converge to the true value function Viewpoint. And now the question is, how can you calculate this? The way we do it is that we notice the similarity between that and our original Bellman equations. So what we have for policy evaluation is that when you have dynamics P, and R pi is the reverse of policy pi on the reverse function R, this form that I minus gamma P inverse times R pi is giving us the value function of policy pi under dynamics P and R. So we can exploit this to calculate each iteration of value OSVI. We have I minus gamma P pi inverse there, so we consider the approximate dynamics P hat. And the trick is that we think about the second term as some auxiliary and reward function r bar vk. Note that it has some dependence on vk apart from constants of the problem, so we have added a subscript vk to our notation. And because of this connection, we see that each new value function that OSPI calculates, vk plus 1, is actually value of policy pi in a new whole MDP that has dynamics p hat, an approximate model, and this new reward function that you see. And that's how the algorithm works. For any value function v, we define this auxiliary reward function r bar v as r plus gamma p d minus gamma p hat d. That gives us the reward for any state action pair. And one thing to note is that you can get this with just one query to P, because we only have one dependence P in our R bar, and that's obtainable with just one query. Once you have got your reward with one query, the new value function is solving the MDP with dynamics P hat and rewards R bar. Okay. Everything cool? One thing you notice is that every value function that OSPI calculates is a result of planning with the wrong dynamics p hat. But as I said, we are converging to the true value function v pi. Because of that, I want to think about R bar this way, that you have the original rewards of the environment R right there. And because of that modification of adding the second term to it, you have changed the reward such that the value functions you calculate become accurate. And I'm going to call that term error correction. And the interesting part is that if vk in your error correction term is the true solution v pi, you are going to get perfect correction, as in the sense that the MDP with the auxiliary reward and approximate dynamics will give you the correct solution. So you have corrected the error of p hat completely and you're good. But we don't have v pi. That's what we're trying to find. And the second property is that if vk is getting closer to v pi and is closer to v pi, your error correction is getting better and better. And so that leads to better value function, and that cycle goes on. This was for policy evaluation. The main difference in control is that we no longer have a system of linear equations. Bellman equations for control are not linear. Here we are lucky that you can extend policy evaluation to control just the way we did it for value iteration. In value iteration, we have the Bellman operator of policy pi being applied at each iteration. And the way we extend this to control is that we just maximize the target value function over all the policies that you consider in your policy evaluation. And we can apply the same principle here, and instead of assigning value of policy, some specific policy in the new MDP as our new value function, we maximize over all policies to get the new value function. Right? And when you are maximizing over policies, you get the largest value function, you're basically talking about the optimal value function in that MDP. So everything is the same. Instead, when you're solving the MDP, you're not doing policy evaluation in the new MDP, you're doing control in the new MDP. This gives us the overview of OSPI. At each iteration K, you first query the true dynamics P, and based on that, you build your reward function R bar VK. Now you have a new MDP with dynamics P hat and reward function R bar VK that you need to solve. And you solve it to get the new value. So VK plus 1 in policy evaluation is doing policy evaluation in this new MDP. And for control, it's doing control in this new MDP, and also the policy that you're reporting is the optimal policy in the new MDP with correction. One thing I want to emphasize here is that OSVI does only one query to P at each iteration, just like what value iteration was done. So it is fair to compare OSVI with value iteration in terms of query, because in terms of iterations, because they have the same cost per iteration. I think it's good to see some visualization of how the whole system is working. I'm sorry.
I'm not sure I completely understand this value iteration part of the algorithm with control.
Here?
Yeah, that's like, yeah.
Or,
Yeah, symbolically, I do understand what's going on. Next slide, there was something. Oh, you call it restart.
So yeah, maybe I should explain the notation. So when working this notation means you calculate v pi under dynamics p hat and this reward function here. And this means you calculate the optimal value function under dynamics p hat and this reward function. Obviously on this dynamics and reward.
What I didn't get is that for policy evaluation we had p pi and p hat pi. Is that not? And can we go back to policy evaluation?
Or
With the R bar and whatnot? Maybe I just missed that. Yeah, like see, like there's p pi and p hat pi, and those they're gone.
so the pi on superscript, you mean?
Yeah.
Yeah. So what
Like
happens?
There was a lead there.
So if you define your reward function here like this, and you look at the rewards of positive pi under this reward function, it will be just some superscript p added where.
I understand that. Okay. All right, so you're kind of like reasoning with homology here that this should work. I mean, yeah, like we kind of split the nonlinear operator in a way that like was funky a bit.
And so like splitting the calculations there.
No, what I mean is that for validation you have max. We kind of moved it outside and
yeah, like I think we're kind of lucky that this worked to just do what we did in value iteration and get control OSVI like this. Because
to the V pi. So the format, what's the definition of V pi, P hat, R, bar, V?
so it's value function plus pi under this dynamics and this reward.
But the police is kind of like first applied to that reward as well. Yeah. Kind of. Okay. Somehow.
Yeah, maybe we can see the visualization. And
Sure.
so
I guess there were no claims about that this works. But the other is.
Yeah, that was my question.
No claims that this automatically speeds up things yet. It's going to come.
Yeah.
Right?
And you just before people want it, like I just showed those two and what's going on in 2A and 2B.
So we are solving two problems. One is control problem when you're aiming to get optimal value function, and this policy evaluation we only want like via pi. And there are two versions of algorithm. So if your problem is policy evaluation, you just do A.
Is that the connection? You're back on.
Yeah.
Again, it makes sense.
Yeah.
I thought those were two steps. And then
Yeah.
yeah.
So we can see this in action in two-state MDP, just a very simple MDP that we want to do policy evaluation on. The cool thing about having an MDP this small is that each value function is basically two numbers, the value that assigns to state 0 and the value that assigns to state 1, right? And because of this, you can represent each value function on a 2D plane. we just pick V0 to be the x-axis, V1 to be y-axis, and now each value function is a point on this 2D plane. So we're starting from some V0, for example, here V0 is assigning 0 to both states, and we want to find V pi that is value function of positive pi in this end. What value iteration does is that it applies the Bellman operator iteratively to go from V0 to V pi. Each blue arrow here is one application of Bellman operator that has cost 1 query. And you can see that it starts from V0, slowly converges to V pi. And now let's see what OSVI does. We are at V0, and as I said, we query P wants to get PV0. Then we use the result of this query to calculate R bar of V0. So we have PV0, you add R plus gamma P hat V0, and I'm assuming V bar and P hats are accessible at no cost. So this step is doable. And now to get V1, you need to solve an MDP with dynamics P hat and reverse R bar V0. How do we do that? We have an MDP to solve, so we can do value iteration. And because the dynamics and reverse are different, we have a different Bellman operator here that has dynamics P hat and R bar V0 because we're solving an MDP with this dynamics.
Say query for every single state action.
Yes.
You have one.
So yeah, so we apply this Bellman operator in the new MDP a lot of times. So that we solve the MDP, we reach V1, and this transition from V0 V1 is one OSVI update that has cost us 1 query. We do it again. We are at V1. We query V1 to get PV1. Then we have a new reward function R bar V1 that gives us a new MDP to solve and get V2. To solve this new MDP, we have the Bellman operator in this new MDP, apply a lot of times until convergence. Solve V2, and this new transition is the second iteration of OSVI. And if you do this iteratively, this is how the path of two algorithms look like in this example. And you can see that we're converging faster than that. So in the paper, we do LN supremum norm and weighted LP norm convergence analysis for the approximate form of this algorithm, where we assume some error is happening at each iteration of OSVI. And that involves a good amount of concentration coefficients, but the main message is the convergence rate that we achieve. And that looks like something like this. We have the rate being gamma over 1 minus gamma times some distance between the two transition dynamics. And that distance in supremum norm results are maximum of total variation distance between distributions of two dynamics. And weighted LP norms, that's a weighted chi-square divergence between the models. And we get that for both policy evaluation and control, our error reduces with the order of eta to the power of k. The consequence is that our convergence rate is now dependent on the model, which has upsides and downsides. The upside is that when you have a very accurate model, this can be, eta can be arbitrarily close to 0, and you can converge very fast. The downside is that if your model is very bad, and that's eta can actually become larger than 1, and we actually see that OSVI does not converge in all scenarios. So that's the downside of having this dependence on the model. One thing I want to talk about is that we can see that the convergence rate we're getting is very different to value iteration. It's good to think about why did this happen. And I want to argue that we are using P in a fundamentally different way than the conventional value iteration. In value iteration, at each iteration, we are using P to apply one Bellman operator. And intuitively, that's propagating the values of the next states back to our current state. And if you want to have a correct value function at any state, you need to propagate the values from all the states in the future with longer horizon enough back to your state so that you have a good approximation of expected return. And because of that, the number of queries of value iteration very roughly and intuitively depends on the horizon. If you have gamma close to 1, your effective horizon of problem is larger and you have a slower convergence. Very differently, in OSVI, we are using P to calculate error correction temps. So you need a query whenever you want to improve your error correction. So again, very intuitively speaking, the number of queries depends on how many times you need to improve your error correction, and that depends on the error in the model. So your convergence rate becomes smaller when your model is more accurate. Yeah.
If P hat is equal to P, I don't understand that.
Yeah, that's we actually converge in one iteration. Okay. So
You're very, very lucky because you can query P hat infinite times. You just see that no one is going to call you a cheater for just giving this free pass. P hat is free. You solve P hat, but you happen to solve P. Because they are equal.
yeah, so the auxiliary reward function becomes original reward. These two terms cancel out and can equal P hat.
Yes, but I thought it will recover the value iteration.
With zero cost because you only use P hat.
Yeah, I think it's not.
P hat.
We need faster here to go through these. Yeah. The next thing we do is to just introduce the algorithm. We don't do theory on this, and that's to generalize the setting where we only have samples from P. The main difference you need to make is that instead of having the R bar and PV value given to you at all state action pairs at once with one query, you need to use the samples to get your R bar. And this is very similar to what we do when we want to get Q-learning from value iteration. You just do stochastic approximation for the PV term. And that's exactly what we do. We maintain some reward function album, and with each sample, we can have an unbiased estimator of the targets using the next state sample here, and we update R bar at each iteration. And the value function we get is pretty much similar to it, so just to plan with P hat and this R. And now that you have some samples, you may also want to update your model to be more close to model basic. In the end, I have some results. We have a 6x6 grid world environment here, and you can see the Q-learning return on the right-hand side and value function error of value iteration on the left side, both converging very nicely. But what we do is that we consider a perturbed model. So our model is the average between true dynamics and uniform distribution. So a pretty wrong model. And what happens is that when you're doing dyno with this wrong model, you're not converging to the true value function policy. So you will have some non-diminishing error in your policy. Same for value iteration, you will have some constant error when you do that. The interesting part happens when you do OSVI. So in value iteration, even with the wrong model, it converges to the true value function, and it can do it faster than value iteration because it's benefiting from the model. Same goes for the sample-based scenario. It is converging to the true value function, unlike dyno, and it's showing better sample complexity than Q-learning. I think that's a very exciting results to get, and showing maybe we can improve the robustness of our model-based RL algorithm with some error correction terms like this, and still benefit from wrong models. And that was it. In summary, we used the model that was inaccurate without suffering from its error. And some obvious next steps are to look at this multi-fidelity problem of having two dynamics P and P hat with different costs and accuracies more. It was just one of the first works on this. And also, you may think about how you can connect this query complexity to sample complexity. And that's all. Thank you for your attention.
Yeah, so very interesting. Very cool. I'm wondering, there isn't a way barking up the wrong tree, or I feel that there is some, yeah, like uneasy feelings about this whole thing, because I want to use the model because I cannot afford to access those state action pairs. I need to reduce the complexity of my algorithms to get away from there. Okay? So I use a model. So I am going to introduce a misspecification, or like I suffer a misspecification error because of that.
Right.
And yeah, it would be like in lean stock, we have seen that we're fighting really hard to get to reduce the blow up of misspecification error when trying to compute an optimal policy or just optimal action in the case of bandits. Why keeping simple complexity polynomial? And here it seems that the suggestion is that, okay, you have this wrong model, you should still aim for computing the optimal solution. So you can aim for that, but isn't that going to lead inevitable to, just you have to look at all the state action pairs at the end. So we had these lower bounds before, let's say in linked store, that was saying that there is a huge cost to trying to reduce the dependence on the specification cost. So is that going like it
So-
appears that this is going in the
I think what's happening here is that we have some concentration coefficients. So you still need a good coverage of accuracy in your model not everywhere, but some reachability forms.
I'm not sure I understand how concentrability is going to save us, but I will think about it.
So you like, it's not that you can freely get information from all the state action pairs, and it's gonna be corrected. You need good query accuracy on those state action pairs, something like that.
You capture the PV for orders.
Yes, so the algorithm is,
So yeah, like there was this idealized algorithm that was analyzed, but later on I assume you want to extend blah blah blah. And
Right.
I'm kind of questioning whether by doing so you're gonna keep the same barriers, and then the approach kind of like what is it going to give us, right? At the end, like when we try to implement it with queries which are reasonable.
my guess is that it may not help correcting the error of unseen state action pairs, but there are some states that are reachable you have samples from, but due to like limited capacity of the model will always be wrong, no matter how many samples you have on that. And here you can adjust for that inaccuracy in your reward function and be fine.
Definitely very interesting. Just
Yeah, so it's
but like yeah, good.
So it's a bit of a follow-up to that. But I guess what you're saying is like this concentrability that shows up. It's basically like when you do this planning, you take the hat and this corrected reward function, and then you get some policy out of it. And then you use that policy in the next update, like on the V that is set to the real environment, right? And so the question is like the states that you see while doing that planning, like if you do it approximately, and are you like how different those are, right? So I guess what I'm trying to say is that somehow you're getting a bound, like depending on the difference between P hat and P. But there is more to it because the actual concentrability, which also implicitly shows up in your bound, depends on how P hat is different.
Yes, so that's part of the rate. So it's not just part of the error propagation. So
yeah, so P hat has to be such that if you approximate planning using one step of this thing, then it gives you the correct state distribution so that you can then do one or step in down and do.
can you repeat the second part?
So the difference between P hat and P, not just the norm of a difference, but the actual difference between them, is controlling what data you are gathering at each step. And then the of that data affects the convergence rate of the outer loop, right? The outer plan.
So when you say distribution of data, is it the starting state action pairs or like initial or the next state or sampling?
So let's say I'm looking at the second algorithm, like the diagram kind of algorithm, where you had a P hat that we're estimating based on the data you have seen so far.
Right.
So now the accuracy of that P hat depends on which data.
Exactly.
And the distribution of the data that you see depends on the policy that you take from coming from the previous round.
Yeah, we haven't considered exploration part of it, so we just assume some weighted error of the, between P and P hats is reduced, and we have good coverage on that row.
Yeah. So actually, you use the P hat here. This the matrix in problem is that the best one is not which is function the P. I mean,
Oh, you have to speed up.
in the matrix speed algorithm, that's the solution. Maybe not the one which is you are using. I mean, in A. But for here,
It might not be the best splitting.
so I'm really curious about that, how that reflects in your community.
And like if there are better splittings,
Yeah.
so if I go, I guess I don't have the splitting, but the convergence rate of splitting depends on the spectral radius of M inverse N. That's the result that we have. And the way you can make it small is to make N as small as possible. Here, N, where is that? So here, N is gamma P minus gamma P hat.
Yeah, so yeah, that's the thing.
Yeah.
Can go back one slide, please?
One slide before.
Yeah. Right, you have the model errors.
Here,
Exactly.
yeah.
It seems like you said this error will depend on model error, right?
This rate depends on model.
Yeah. But actually, what I'm asking that the optimal P hat may be not the true model.
So you,
So I'm thinking maybe the best one should be that instead of the true model.
so you may have positive model error and still get
Yeah, so that's
convergence
the
rate.
Yeah.
Yeah. I think that's true. So you can, I have a high, they give a high chance that with better analysis, we can reduce it to some form of value error, model error. And you may include some wrong models in the family of models that converge in one step. But we are wanted to have some standard model error.
Not wrong model, but another model, which gives you the best convergence rate. And the model error is the line.
So even if you're fitting the model, maybe you don't want to just like fit it empirically, but want to take into account the whole thing, operator splitting.
So use the loss here to how you're learning them.
Yeah.
model.
optimize the approximate model
Mhm.
in terms of the capacity and the convergence rate.
Exactly. So that is the one which uses the best. And the rate is not depends on model.
That's
Great
interesting.
question. Yeah.
Yeah, we haven't done that. That's a good question.
Anyways, related question. So we saw that this model error over the 1 minus gamma can be larger than 1.
Right.
That wouldn't be very good. Can we design an algorithm that doesn't ever have this property? Because I mean, like we could have used value iteration. So it's like adapting to, you know, like you see model error is big, then oh, don't use this approximate model. Maybe it's related to what Bo is also saying that even okay, not related, but like if you have p hat and then p, you can interpolate, let's say, linearly between p hat and p, and you expect that you should be able to get an algorithm which automatically gets the best of both worlds and maybe something better.
So one thing you can adjust is the now. So when you solve the new MDP, I assume that you solve it until convergence. So you use p hat as much as possible.
Yeah.
If you only do finite number of Bellman operators in that MDP, you're somehow interpolating how much you're using p hat.
But somehow the algorithm should monitor how well it's doing and switch to the best possible way.
Right. I don't know how to do it, but I think you need some uncertainty estimation to know how bad your model is.
You can run the two algorithms in parallel and then just choose a better.
Yes,
Like
some
I
meta learning approaches.
You can call it like that. All right.
So,
Your algorithms always converge, and this error only shows up in the rate.
You need to repeat the question.
and so yes, so model error only appears in the rate here.
You always have convergence.
Yes, as long as this rate remains less than 1, you converge to the true value function.
I mean, if you say this model error is allowed to do have convergence.
No, it diverges. So this auxiliary reward starts to just increase, things start to explode.
This expression is very stringent for large discount.
So we also don't like large discount factors. As you can see, we have this dependence of 1 over 1 minus gamma here. Yeah, when you increase gamma, your requirement on model errors become more strict as well. That's it.
So if it starts diverging, that is the point you can detect.
Yeah, like if you grow bigger than age, whatever 1 minus gamma, you should stop what you're doing,
Yeah, you can always clip your value function.
and then you just like stay big. That's not a good solution, right?
Yeah, you will be at some random.
You probably want to do something more clever. Anyway.
Yeah.
Okay. Any other public questions? All right. No more questions then. Thank you.
Thank you.